So, welcome back. This is the next lecture on stress tensor. So, in the last lecture we have categorically seen what is Cauchy's stress sigma, and we have seen that definition of sigma indicates what is the internal force that gets developed within on a plane or within a body at a point due to some action of external forces. Now, what actually is sigma? In fact, sigma is a stress tensor. So, Cauchy stress, it can be considered as a tensor. So, now we are going to define a new term, what is known as tensor. If you want to study or if you want to do modeling in continuum mechanics, as the complexity of the problem increases, it is always convenient to define what is known as tensor. And we have already stated stress is a tensor quantity. Now, what is a tensor? We know what are scalars, we know what are vectors. So, tensor is also a similar kind of quantity. So, why tensor? Because it is very convenient to express stress as a tensor. In short, stress itself is a tensor. In simple terms, we can say that tensor can be defined as a quantity with magnitude and multiple spatial directions. So, possibly you will think like, what is the difference between a tensor and a vector? Vector also has a magnitude and a direction, but we will see that vector has magnitude, but it will have only one direction, whereas in the case of tensor multiple directions are there. So, that is the essential difference, and tensor is a more general term, and the subsets of tensor are scalar, vector and any other tensor of higher order. So, different tensors which are popularly used are, yes, that is what I told. The first one is scalar. The simplest tensor is scalar and it is called zero order tensor. A quantity which have only magnitude and zero direction. Scalar, we all of us know that it does not have any direction, it has only magnitude. So, we call it as zero direction. And zero order tensor, which is a scalar, have 3 raised to 0, where 0 represents the number of direction. So, 3 raised to 0 equal to 1 element, and that is true. It is merely a number which shows the magnitude. So, scalar is a zero order tensor. The second one is vector, which is the first order tensor. Vector is a quantity which have magnitude and one direction. You can see that vector has only one direction. Accordingly, the number of elements will be 3 raised to 1, which is equal to 3 elements. So, if you have x, y, z axis, you have vector in 3 different directions. So, that is possible. So, that is what it means, it has 3 elements. So, it has one direction, every vector it is associated with only one direction, and it has 3 raised to 1, which is 3 elements. And specifically Cauchy's stress is a second order tensor. Why? Cauchy's stress sigma have magnitude and 2 directions. Now, what are these 2 directions? Now, we will see it specifically how these 2 directions comes into picture when you define a stress component, and it is very easy also. If you remember Cauchy's stress, we represent it as sigma x x or sigma x y. So, there are 2 symbols associated, and that is why it is always associated with 2 directions. It is associated with on which plane it acts. That means the normal to that particular plane. It is also dependent on which direction that particular traction acts. So, we will discuss that a bit later. Only to specify here is Cauchy's stress is a second order tensor. It has magnitude and it has two directions. So, this is second order tensor and it has 3 square equal to 9 elements, which we have already seen in the Cauchy stress tensor. There are 9 elements, and the second order tensor, it linearly maps two vectors. That also we have seen. We have seen that T is sigma transpose of n. So, it linearly transforms two vectors, that is Cauchy's formula. Now, some aspects of tensor, to be very specific, this may not be useful, but then this is important to understand the tensor. Let us say there are two vectors u and v. A tensor T is a second order tensor if it linearly maps vector v to u, as can be shown here, and the second order tensor satisfies the properties of linear transformation. So, this is what is being written. T maps v to u, or there is a linear mapping of v to u. If you compare this with Cauchy's formula, it is more or less the same thing. That is how we define Cauchy's stress tensor is a second order tensor. Having said that, now the next job is to interpret the components of Cauchy's stress tensor. We know that there are 9 elements. Now, what are these 9 elements? What does it represent? So, for that we need to define the Cartesian coordinate. So, you have a Cartesian coordinate x, y and z, and to make it simple, a control volume is also shown. Control volume is a very common terminology which is used in continuum mechanics or any other form of mechanics. In fact, this control volume is not required, but to make things simple and for one to understand, it has been shown. So, we have a Cartesian coordinate x, y, z. This is positive x direction, this is positive y, and this is positive z. That is also important here. So, you consider positive x plane. Now, x is an axis. What is meant by x plane? It means the plane on which x direction is the normal to that plane. So, that is what it is written here, the plane whose normal is in positive x direction. So, it is called positive x plane. So, what will be negative x plane? The negative x plane will be here, because the outward normal to this plane is in the negative x direction. So, this is negative x plane. So, you need to understand this very carefully. Consider positive x plane. So, we are talking about this particular plane, that is positive x plane. Why? Because normal to this particular plane x, this is the yz plane, this is y, this is z. So, this plane is yz plane. Now, for this yz plane, the normal is in the direction of x. So, that is what it means. So, x plane means positive x plane means yz plane, which is shown here. So, positive x, negative x plane, both are there. Now, we will come back to Cauchy's formula and Cauchy's stress sigma. So, now normal vector to x plane is positive x direction. Please understand, the normal vector to x plane. So, this is the x plane, the normal is x. So, you can easily write what is the normal vector. So, this is the normal vector. So, for x direction it is 1 0 0. So, nt is given in this manner, and similarly for y it will be 0 1 0, and for z it is 0 0 1. So, normal vector to x plane is defined, that is n transpose is given. Now, what are the components of traction vector Tx, Ty and Tz? You already have this to be, that is Tx, Ty, Tz is equal to sigma and n. So, if you substitute the value of n, that is for positive x plane 1 0 0 here. So, it will be 1 0 0, and do the matrix operation, you will see that Tx is equal to sigma xx, Ty will be equal to sigma xy. So, this is sigma xx, sigma xy. So, Ty will be equal to sigma xy and Tz is equal to sigma xz. So, what does it mean? It means that the components which are present in Cauchy stress tensor, these are components of traction vector in a given direction. So, if you see, you can see that sigma xx is the x component of traction vector on x plane. So, there are two references which are coming, and that is why we said that there are two directions. It is the x component, that is the traction vector is in the x direction and it is acting on x plane. So, there are two things which are coming. Similarly, you have sigma xy. Sigma xy is the y component of traction vector acting on x plane. Similarly, you have z component of traction vector acting on x plane. Similarly, other components of Cauchy stress tensor can be identified based on Cauchy's formula. So, that is what is the meaning of each of the terms which are present in the Cauchy stress. It is nothing but the components of traction vector acting in specific direction. So, the component of Cauchy stress tensor in general is sigma ij. It is the j component of traction vector. It can be x, it can be y, it can be z. So, it is the j component of traction vector acting on ith plane. So, first index I, it shows which plane it is associated with, which plane means which is the normal, and j is the direction of that component, direction of the component of traction vector. So, I is the plane on which traction is considered, j is the direction in which the traction component is considered. So, we can see the overall representation of Cauchy's stress tensor. So, first is stresses acting on x plane. Now, which is the x plane? This is the x plane. So, there are two x plane, this is negative x and this is positive x. So, what are the stresses which are acting? We have sigma xx in the direction of x. So, all of them are acting on x plane. Then we have sigma xy and sigma xz. Similarly, on the other side, other plane, that is negative x plane, we have sigma xy, sigma xz and sigma xx. It is identical, but it is on the other side. Then we have stresses on y plane. Now, what is meant by y plane? A plane with y direction as the normal. So, you are talking about this and this. So, you have positive y and this is negative y. Similarly, so in this you have sigma yy, which is the direction in the direction of y, and you have sigma yx, sigma yz, similarly sigma yx and sigma yz. Then we have stresses acting on z plane. what are the stresses acting on z plane, and what are the z plane? This is positive z plane and this is negative z plane, and the stresses acting are sigma zz, sigma zx, sigma zy. Similarly, here also you have sigma zz, sigma zx and sigma zy. So, these are the representation of the components of Cauchy stress on a given control volume. So, all these stress components are acting at a point. Now, we need to keep in mind, since I have shown a control volume in the figure, and that is only for understanding how the stresses are oriented, otherwise it does not serve any purpose. We need to still understand that whatever stress components are there in Cauchy's stress tensor, it is acting at a point, and the control volume, the cuboid, is shown only to indicate the plane on which it is acting. So, that notion we should not forget. So, it is a stress acting at a point. Now, having said that, we need to now define some sort of sign convention of Cauchy stress tensor. So, the given sign conventions are the traction components on positive plane. So, now we have already marked what is a positive plane. So, the traction component on positive plane acting in the positive direction means the direction of x, y, z, which is in the positive direction. So, is positive. So, you have positive plane and the traction component is acting in the positive direction. So, it is positive. Similarly, if you have a positive plane and the traction component is acting in negative direction, so it is negative. For negative plane, if the plane is negative and the traction component is acting in negative direction, so it is positive. And the final case is negative plane, traction component direction is positive direction, it is negative. So, this is one sign convention. You can see that there are numerous sign conventions which are available, and one may use at his convenience, but if you follow one sign convention, you need to follow it for throughout. So, this is one convenient way of defining sign convention. There are sign conventions which are available based on moment also. Sometimes it may be difficult to understand. So, this is very easy and very easy to define as well. One example is given here. So, this is the positive x plane and the stresses acting are sigma xx, sigma xy and sigma xz. Now, if you consider sigma xx, this is acting on a positive x plane and sigma xx is acting in the positive x direction. So, that is why it is positive. Similarly, sigma xy and sigma xz. Now, consider the case of negative x plane. If you consider sigma xy, this is a negative plane, negative x plane, whereas this is acting in positive y direction. So, negative plane, positive y direction, so it is negative. Similarly, all the stress components sign can be assigned. So, this is the sign convention of Cauchy stress tensor. So, what are the summary that we have understood till now? There are three normal components or normal stresses: sigma xx, sigma yy and sigma zz. You can see that in this figure you have sigma xx, sigma yy and sigma zz. These are acting in the same direction as that of normal. So, there are three normal components or normal stresses: sigma xx, sigma yy, sigma zz, or it is merely stated as sigma x, sigma y, sigma z, which is a common terminology which we normally use in mechanics. There are 6 shear components or shear stresses, to be very specific, all indices where I not equal to j. Here it is I equal to j, here I not equal to j. So, these are shear components of traction or shear stresses. It is written either in sigma form or in tau form. Cauchy stress tensor, a second order tensor, quantifies the internal force distribution in a body at a given position and time corresponding to a given deformation. Why time is important? Because we are considering the condition corresponding to a given deformation. And internal forces which that gets developed, it follows the basic laws of mechanics. Now, one particular aspect why stress at a point that information is needed is to define the equilibrium equation. So, it is a application of why you need to have the knowledge of stress at a point. Now, stress at a point is very important to define the equilibrium equation. As we have seen in the beginning, we have seen that there are certain requirements which need to be satisfied, like equilibrium condition, the compatibility condition and so on. Now, for defining the equilibrium condition, we need to specify equilibrium equation. I will not go into the derivation of these equilibrium equation, it is very basic and which is mostly seen by most of you. So, by considering a given control volume, the equilibrium equation can be represented as follows, and you can see that the components of equilibrium equations are the stress tensor components. The only new term is gamma, where gamma is the self weight or the gravity stress which acts in the z direction or in the vertical direction. And to be very specific, stresses are in terms of total stresses in this particular equation. It is invariably necessary to have the knowledge of stress at a point for defining equilibrium condition. Now, based on equilibrium, we can say that tau yx is equal to tau xy, tau yz equal to tau zy and tau zx equal to tau xz. Therefore, the stress tensor is represented by 6 independent stress components. There are 9 components in the Cauchy stress tensor. Just because of this condition, we have 6 independent stress components, and they are 3 normal stresses sigma x, sigma y, sigma z, and 3 shear stresses tau xy, tau yz and tau zx, where tau xy is equal to tau yx. So, this is what it is. So, that is how it boils down to 6 independent stress components. So, the final summary of what we learned in this particular lecture is Cauchy stress sigma is a second order tensor. The elements of stress tensor represents components of traction acting on 3 orthogonal planes according to a given Cartesian coordinate. Sigma ij means j component of traction vector acting on ith plane. Stress tensor sigma has 3 normal stress components and 6 shear stress components. But based on equilibrium, there are 6 independent stresses where 3 normal and 3 shear stresses. All the stress components are acting at a point which is a very relevant point and which is very important. The components of sigma depends on coordinate axis. Please note here, as such sigma, it is not dependent on coordinate axis, but the components of sigma, I mean to say sigma x, sigma xy, those are the components or the traction vector components, they are dependent on the coordinate axis. So, there is a distinction which need to be very clear. One should not get confused with sigma as a whole and the components of sigma. Sigma as a whole, it is not dependent on any axis, but the components of sigma keeps changing, but the overall sigma representation of internal force remains the same. Depending on the reference axis, the components magnitude or value keeps changing. Stress tensor sigma at any point in the body defines the internal force distribution of a body. So, this is all about this particular lecture. We will see in the next lecture.